And welcome back. As we go ahead and continue our topic of data structure, we're introducing a new thing, which is that of the hash table. This is going to be building off of what we learned with linked lists, but it's going to have a couple advantages that we can use in comparison to the other structures we've learned so far. So with hash tables, these are also known as a hash map, but they're data structures that efficiently store and retrieve data from memory. There are many ways to construct a hash table, and the way we're going to do this, we're going to use an array in combination with single linked lists. And if you recall, we have seen that a linked list generally requires linear, or big O of n, steps to determine if a target is in the list. In contrast, a hash table has potential to execute a fixed number of steps to look up a target regardless of size n. And we see that a constant time lookup is big O of 1, which is kind of our best ideal scenario. However, the hash table that we're going to look at today may require additional n steps, but such a case is not typical going to happen because, again, big O runtime is looking at a 1, which is our most ideal situation that we can get here. So when we actually look at the hash function, an object is stored in a hash table by first associating it with the key. Once we're given the key, we can then retrieve the object, and ideally that key is unique to each object. If the object has no intrinsically unique key, then we can use a hash function to compute one. In most cases, the hash function is going to compute a number. So for example, let's say a hash table is being used to store a dictionary of words. Such a hash table might be useful for things like making a spell checker. Words missing from the hash table might not be spelled correctly. Now, of course, as we mentioned, there are things that we kind of have to be aware of when we start looking at these keys, and the first is collision and chaining. If we will construct this hash table with a fixed array, we're going to say that each array element is going to reference, let's say, a linked list. The key computed by the hash function, therefore, will map to the index of the array, and the actual data will be stored in a linked list at the hash values index. So when we actually look at how this is going to work, you can see that we have a similar kind of setup here, how we worked with our linked list. So this, of course, is using a fixed array of 10 entries here. Initially, each entry of the array hash array contains a reference to an empty singly linked list. First, we add the word, let's say, cat, which has been assigned a key or hash value of 2. And you can see it's ending up here in index 2. Next, we're going to assign, let's say, dog and bird, which are assigned the hash values of 4 and 7, respectively. Now, each of these strings is inserted as the head of the linked list, using the hash value as the index in that array. And finally, if you look, we can add one more. We'll say it's turtle, but we're going to add it at a hash of 2. And we have 2 things now sitting here at 2. What does that mean? Well, this is getting to where we start having to address collisions. Because cat is already stored at index 2, we have what's known as a collision. Both turtle and cat map to that same index in the array. When this occurs in a hash table with chaining, we simply insert the new node onto the existing linked list. An example, there are now 2 nodes, therefore, at index 2. We have turtle and we have cat. So if I want to retrieve a value from the hash table, we first compute the hash value of the target. Next, we search the linked list that's stored at the hash array, hash value, for the target using an iterator to sequentially search the linked list. If the target is not found in this linked list, then the target is not stored in the hash table. And if the size of the linked list is too small, well, then the retrieval process is going to be quick because, less items you have, less items you have to search through. So, in these examples, everything we've seen so far are strings. And so, obviously, we can have a function for this. So, a simple way to compute a numeric hash value for a string is to sum the ASCII value of every character in the string and then compute the modulus, or the remainder, of the sum using the size of the fixed array. So, if we want to look at some code to how to compute that hash value, we can use this method right here, private int compute hash string s. Int hash is 0. And then we have a simple for loop that is going to start at I of 0. So this is pretty much starting as the beginning index, if you will, of that string. And then we go through the length of the string, I plus plus. And so then hash plus equals s.char at I. Of course, that is pulling that string apart character by character. And then you look, we'll get return hash modulus size. Size is 10 in our example. Okay. And don't forget, again, this is a modulus operator. One you may not be as familiar with because we don't use it as often, but remember that just means find the remainder. Now, looking at the hash function for strings, if we actually go ahead and start picking this apart, let's say the ASCII codes for the string dog are as follows. So we'd say, well, D is greater than 100, 0 or O is going to map to 111, and G is going to map to 103. So if you actually look in the ASCII table, this is the value 100, value 111, value 103. Now the hash function, therefore, is computed as follows. So we're saying sum of 100 plus 111 plus 103 gives us a value of 314. So then the hash is simply the sum with the modulus operator of 10. Remember, our array is size 10, so we say 314 mod 10, we get a remainder of 4. So we first compute an unbounded value, the sum of the ASCII values in the string, and that's going to lead us to our mapping here. However, if you think about the array that we have here, it's only designed to hold a finite number of elements. In this case, it was 10. If we want to scale the sum to the size array, we compute the modulus of the sum with respect to the size array, which again was 10. In practice, the size array is generally a prime number that's larger than the number of items that's going to be put into the hash table. So for example, let's say we're going to put let's do 10 items here. All right. Well, the next prime number up would be 11, and that would be a better item to use. Now, the computed hash value of 4, in this case, is serving as a fingerprint for the string dog. However, different strings may inadvertently map to the same value. So, for example, we can verify cat is going to map to 2, if you do the math, and that turtle is going to map also to 2. All right, because, again, they're getting those values and how the modulus is working here. It's ended up putting them in the same spot. Now, this, of course, all this mapping and everything that going on is going to lead us back to our conversation about the efficiency of hash tables. The efficiency of our hash table depends upon several factors. The worst case runtime performance occurs if every item inserted in the table has the same hash key. So if we put, let's say, everything at node 2, well, then everything's going to be stored in a single linked list. And with n items, the find operation is going to require big O of n steps. If the items we insert are somewhat random, though, well, the probability that all of them will hash the same key is going to be very unlikely here. In contrast, our best runtime performance occurs if every item has its different hash key. So if every one is plugged to its own piece in that array, this means there's going to be no collisions, and the find operation is going to require constant or big O of 1 steps because the target will always be the first node within that linked list. Now, if we want to look at decreasing the collisions here, we can do this by having a better hash function. The simple hash function that sums each letter of a string ignores the ordering of letters, for example. The words rat and tar would technically hash to the same value because, if we take the ASCII values and add them up, they're going to be the same. A better hash function for a string is to instead multiply each letter by increasing weight depending upon the position of the word. So, for example, int hash equals 0, and we have our for loop, int starts at 1, goes to the end of the string, and we say hash equals 31 times the hash plus s.char. That 31 times is, of course, adding a weight value here for those positions. Now, all this is, of course, leading to a kind of a time and a space trade-off here of what we want our program to be able to do. Another way that we do this is through the decreasing of collisions is making our hash table bigger. Well, if the hash table, let's say, stores 10,000 entries, but we're only storing 1,000 items, then the probability of collision is much, much smaller than if the hash table array stored only 1,000 entries. However, as you can probably figure out, a drawback to creating an extremely large hash table array is wasted memory. If we have, let's say, only 1,000 items are inserted into that 10,000 entry hash table, then you have at least 9,000 memory locations that are going unused, and this is a space-time trade-off. It's usually possible to increase runtime performance then at the expense of memory space and vice versa. So again, it's going to be a balance. This is things you're going to have to, as a programmer, decide how you want to allocate things so that way they can be the most efficient if efficiency is the goal of your program. And if we come over here, we can go ahead and take a look at that hash table in Eclipse of how this is going to work. Of course, we have our generic linked list 2 object here, so we can, of course, build that singly linked list. In our hash table, you can see we are, of course, calling that right here by creating that hash array. And inside of here, we have code that's actually going to let us do it. And we have a couple methods going to work for us. We have the compute hash method, which we've seen before. We have the contain string, which is, of course, simply just looking to see if it's containing a value within there. And, of course, we have put. And put is simply just going to store or put a string into that hash table. So this is how we actually end up adding those items. And if we look at that here in our demo, this of course is using those codes that we talked about before. So we're going to add dog, cat, and turtle, and bird. And you can look, we have h.put, 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 and we're doing dog, cat, and turtle. And then we are simply just asking whether or not it contains those values. So if I go ahead and get ready to run this program here, we are going to see that it's going to add dog, cat, and turtle. Does it contain dog? True. Does it contain cat? True. Contain turtle? True. Contain bird? True. Contain fish? False. Contain cow? False. Because again, it's just simply checking this structure. This is not anything too new or radical, because again, once you have this hash table set up, it's very easy to implement with a linked list. However, one of the things you have to keep in mind is, again, looking at how you want to create this hash table. We look at our hash table here. We're limiting ourselves to size 10. So if we had more items, we need to come back to this hash table class and modify that. Additionally, when we start thinking about how we want to use this structure, one of the big things is, remember, this is really great when we start looking at, we want to have really efficient programs. But as I mentioned previously, if we want to have a large number of values, obviously this is going to have to increase, and the more you have for values that are being allocated, the more memory and space you're going to need for your program to run efficiently.